Here we'll answer a question about atomic radius. We are given a list of elements, fluorine, rubidium, oxygen, sulfur, and ruthenium, and we are meant to rank them in atomic radius starting from the smallest. The important part here is the periodic trend that determines atomic radius. We can base this off of each element's position on the periodic table. The elements in the upper right part of the table tend to be the smallest, while the elements in the lower left part of the table tend to be the largest. So if we are looking to start with the smallest, we need to look for the one that is in the upper right part of the table. Let's locate the element's positions on the table. Fluorine is located here. Rubidium is located on the opposite end in the lower left. Oxygen is located next to fluorine. Sulfur is located next to oxygen. And ruthenium is somewhere in the middle of the table. So if we want to start with the smallest, let's start in the upper right. The one that is closest to the upper right-hand corner is fluorine. It's going to have the smallest radius of anything in the list. Now notice oxygen and sulfur are both pretty close to fluorine, but oxygen is on the second row of the periodic table, which we'll label with a 2. Sulfur is on the third row of the table. We'll label that with a 3. Now to tell between them, to see which one's the smallest, we have to remember that having 2 levels is smaller than having 3 levels. That extra level will take up more room. Therefore, oxygen comes next, and sulfur comes after that. The 2 left are ruthenium and rubidium. Ruthenium is definitely further to the right than rubidium, so rubidium will be last in the list, and ruthenium will be in between. This question gives us a list of 5 elements and asks us to rank the atoms in terms of their first ionization energy, starting with the smallest ionization energy. First, we'll define ionization energy. Ionization energy is the amount of energy it costs to remove one electron. Now, in general, smaller atoms with high electronegativities tend to have high ionization energy. So the atoms with high electronegativity that tend to be small are the ones in the upper right-hand corner. These will have large ionization energies, abbreviated IE. That means that on the opposite corner in the lower left are the atoms that have low ionization energy. In general, ionization energy will increase as we go to the upper right. So let's check the positions of our elements on the table. We have fluorine. This is in the upper right corner. Rubidium in the lower left. Oxygen next door to fluorine. Sulfur next door to oxygen. And ruthenium near the middle. So our lowest ionization energy will be the one in the lower left corner. That's rubidium. As we move toward the right, ruthenium is next in line. As we continue toward the right, we see that oxygen and sulfur are in the same group. So the one that is lower on the table will have the lower ionization energy. That's sulfur, followed by oxygen. And the highest will be fluorine in the upper right-hand corner. It's also worth mentioning that any configuration ending in P1 or P4 will have lower ionization energy than expected. Let's briefly go over the reason for that phenomenon. Let's take boron, for example. Boron's electron configuration starts with helium, followed by 2s2, 2p1. Now let's take away an electron. This will give us helium 2s2 because we are taking away the p before we touch the s. If we draw an orbital diagram for this, the 2s has 2 electrons and the 2p is completely empty. Now, anytime you have a full subshell, an empty subshell, or a half-filled subshell, you'll have a more stable configuration. Any of these 3 conditions will give us something stable. We can see that stealing this electron out of the 2p leaves us with an empty subshell and a full subshell. That means taking that electron from boron will not be that hard. It will cost less energy than expected. So this will break that periodic trend that we just saw. Boron will be slightly lower than its neighbor to the left. We also observe this for elements that end in P4, such as oxygen. Its configuration starts with helium and has 2s2, 2p4. Let's imagine taking away an electron. This will leave us with helium, 2s2, 2p3. Here's the 2s and the 2p. The 2s has 2 electrons, and we can see that the p has 3 electrons, and this is exactly halfway filled. And therefore, this is more stable than expected. So therefore, stealing from a P4 costs less than we think it will. Now, if we check our periodic table, the elements that would be P1 are anything in 3A. The ones that would end in P4 are anything in 6A. So these 2 groups will be lower in ionization energy than what you would expect. This would have given us problems if nitrogen had been part of that list. It turns out, despite being to the right of nitrogen, oxygen is actually slightly lower in ionization energy than nitrogen. So be careful anytime you see group 5A and 6A in the same question.